University Video Communications, with the sponsorship of Analog Devices, welcomes you to this edition of the Distinguished Lecture Series, Leaders in Computer Science and Electrical Engineering. This presentation, Bipolar Translinear Circuits, explores the remarkably accurate relationship between the collector current and base-emitter voltage of bipolar transistors. This relationship is the foundation for many linear and nonlinear signal processing circuits. Barrie Gilbert has had a distinguished career designing analog circuits since the late 1940s, working on merged logic, the translinear principle, carrier domain devices, electro-optic memories, and optical character recognition systems. He is now a division fellow with Analog Devices, working on a variety of IC projects. Barrie Gilbert.
This is one of millions of crystal sets that were made, perhaps 60 years ago. And it's interesting not only in that it reminds us how far electronics has come in the intervening 60 years, but also because it includes what might be called the genetic stuff of the modern electronics industry, a PN junction. In this case, it's a galena crystal. And as the whisker was wiggled across the surface of the crystal, so the junction came and went. And eventually you found a sweet spot resulting in this nice, clean relationship between current and voltage. We're not going to be too concerned about the behavior of the PN junction in its reverse mode when it's negatively biased, but concentrate rather on the behavior in the forward region where the current increases very steeply with the applied voltage. We begin with this curve showing the relationship between current and voltage, and generally speaking, rectifying junctions have the propensity for conducting in one direction and not in the other. We all know that, of course, but we're going to be focusing on the forward bias region in particular. Here we show a PN junction in forward bias, and we're going to be very interested in the relationship between the voltage and current. Now, we all know this is a nonlinear relationship. What's of special interest is the particular kind of nonlinearity. Here we see the forward region alone. We're not going to be interested at all in the reverse region for the rest of this discussion. And the important relationship is the exponential one between the voltage, the forward voltage applied across the junction, and the current that flows through the junction. This is a more exact representation of that relationship, and it contains a number of interesting features which we need to take note of. The first is that the forward current is proportional to something which we'll call the saturation current. It's very strongly dependent upon temperature, typically increasing by as much as 8% per degree centigrade. And it has a very small value at typical temperatures in the region of 300 degrees Kelvin or 27 degrees centigrade, perhaps in the region of 10 to the minus 16th of an amp, even lower in many cases. So we don't determine I sub s by direct measurement, but rather by inference through the forward voltage. The other thing worth noting here is that the forward voltage is first divided by the thermal voltage, kT upon Q, prior to becoming the argument of the exponential term. Now, if this were a discussion about, say, temperature sensors, we could spend quite a bit of time talking about some of the intriguing aspects of this relationship. We can, for example, turn that expression around and show the forward voltage as a function of the forward current in this way. And whilst at first glance it might look as if the forward voltage should increase with temperature because Vt, kT upon Q, multiplies the logarithmic term, the very strong temperature dependence of the saturation current means that in fact the forward voltage decreases with temperature in the familiar way, typically by 2 millivolts per degree centigrade. Well, we're not going to dwell on that aspect of the junction behavior very much right now. In fact, it's the very point of the translinear approach to design that we can ignore the exact value of the forward voltage in many cases and instead think in terms of the relationship between currents. But I'm jumping ahead a little bit. Let's first look at the behavior of this junction from the point of view of its incremental resistance. It's important to remind you here that the incremental resistance is not a real ohmic resistor. it has no Johnson noise, for example. It's merely a representation of the slope of this exponential function. What we're showing here is the derivative dIF by dVF, which of course is not a resistance but a conductance. Now we're still talking here about a simple two-terminal diode or PN junction, so that's the conductance of the junction. We can find the value very readily because the exponential form is easily differentiated, and we soon discover that the conductance of a two-terminal diode is directly proportional to the forward current. This is the beginning of the translinear notion. Before we consolidate that idea, we'll talk more about transistors working in this mode. But before we do that, we'll note that we can represent that diode as a voltage, Vf equal to Vt log If upon I sub s, and an associated dynamic resistance, Vt upon If. Remember, that is not an ohmic resistor, although later we'll have occasion to refer back to the non-ideal behavior of junctions in which there really is some ohmic resistance there that causes some problems. Now, we're not really too much concerned with diodes. We will come back to them in a moment, but let's look at the behavior of a transistor in its normal active mode, that is, with a reverse bias on the collector junction and a forward bias on the base-emitter junction. Now the relationship of interest is between the collector current, here shown as IC, and the base-emitter voltage, VBE. Once again, it's a very exact exponential relationship with the saturation current I sub s multiplying the exponential term and the thermal voltage Vt being implicated in the argument of the exponential. The Gummel plot shows how that relationship between collector current and base-emitter voltage is very linear on a logarithmic collector current scale over many decades, at least 6 decades, and frequently 8 to 9 decades of current. That's an intriguing aspect of the behavior of bipolar transistors. We also show here the behavior of the base current. I'd like to suggest that you forget everything you've been taught about transistors as current-controlled current sources. That is, the presence of the base current is inevitable and it's unavoidable. We need to deal with it in a practical design, but it's not germane to the concept of transistor behavior, in my view, or at least in the translinear view. Really, the best way to view the transistor, at least for the purposes of this discussion, is as a voltage-controlled current source. So the base current is shown here, and of course the ratio of those two currents is the transistor beta. As you can see in this particular pair of curves, it's the distance between the two lines, which on a logarithmic scale represents the ratio of the currents, is constant until very high currents when the beta begins to fall, and at very low currents when it falls again. But we're not concerned about the base current, we're just concerned with how the collector current bears this exponential relationship to the base-emitter voltage. Just as we could find the derivative of the exponential behavior of the PN junction, we can do just the same thing in the case of the transistor, of course. And now we're talking about the transconductance, the relationship between the collector current and the base-emitter voltage. And this has exactly the same form, except that instead of IF, the forward current in a two-terminal device, we have IC, the collector current of the transistor. Now, the really remarkable thing about this, and it's really the essence of the whole idea, is that the transconductance of a bipolar transistor is a linear function of the collector current. That's very important, and it's out of that basic idea that this whole set of circuits, this class of circuits, arises. The term translinear also has a somewhat different meaning. It relates to the idea that these circuits bridge the gap between the world of purely linear circuits, with all the familiar mathematics of linear networks, and the world of nonlinear circuits. Many times a translinear circuit can be applied in such a way that it's transparent in the sense that its nonlinearity is not really apparent. It's not being utilized. A gain cell might be an example of that. Yet underlying the behavior of this circuit always is this relationship between the transconductance and the collector current. So this is really the most important idea that we're going to encounter. So we can put that in words as follows. As you can see, translinear circuits are those in which the primary function is dependent upon the exponential or logarithmic behavior of PN junctions. Now that's not the original definition of the term translinear, It's a rather more general one. It, you note, does not refer to closed loops of junctions. That's something we'll get around to in a moment. It implies that any time you invoke this linear relationship between collector current and transconductance, you really are depending upon the translinear idea. So, for example, we have here a very familiar circuit, the differential bipolar pair, and the relationship between the difference in output current and the input voltage is invoking the translinear idea behind the bipolar transistor. We don't resort to a knowledge of the beta of the transistor, for example, to determine that relationship. Nor are we too concerned at this point with the fact that the transistors in a practical situation would have ohmic resistance associated with the junctions. The key idea is embodied in the hyperbolic tangent relationship between the collector currents and the difference in the base voltages. Now, this is an example of a translinear circuit of a general kind. I might call this a translinear network. It's not a strictly translinear circuit because there is no closed loop around the junctions. A better example, and in fact the simplest example of a strictly translinear circuit, is the familiar current mirror. Here we have one transistor connected as a diode and the second transistor connected in its normal active mode, and we know from almost inspection that the output current is going to be a linear function of the input current. We can scale the mirror in such a way that the output current is more than or less than the input current. But the important point to note here is that there is a closed loop of two junctions in this case, and this is a strictly translinear circuit, and the important idea here is that suddenly we don't have to concern ourselves with voltages. We really are not at all concerned with the absolute value of the VBE of the transistor in this case, or the two transistors. So in this case we can tell what's going to happen almost by inspection, certainly by familiarity with such a commonplace circuit. However, what about this? Here we have 7 transistors, 5 of which are wired as diodes, the remaining 2 as transistors in their normal active mode. We don't show where the collector is taken, but it's presumed to be taken to a positive supply to bias the collectors in their reverse mode. We have 2 inputs now, I sub x and I sub y, and an output, I sub z. Now, can we tell by inspection what I sub z is? It might be hard if we hadn't first discovered the principle behind the analysis of this kind of circuit, the translinear principle, which is what we're going to do next. But before we do that, let's look at one more practical example, which is a diode bridge. Now, in this case, we have 2 currents, IB at the top and ID at the bottom, and a third current, IA, which we can think of as a signal. IB and ID always flow in the same direction. IA can flow in either direction. It's a bipolar current. Now, of course, the load current is simply the linear algebraic sum of the 3 currents. So we don't need any special technique to find the value of IC. However, we might be interested in knowing, let's say, the dynamic resistance from the input point to the output. This might be the case, for example, in the use of this diode bridge in a high-frequency sampling gate, where the dynamic resistance would affect the speed of the gate. Now, to analyze the behavior of this bridge, we must consider, for the time being, both the voltages and the currents. The voltages associated with each of the currents are related by the junction equation, which we've seen already. And furthermore, the voltages around any closed loop must, of course, sum to 0. So we have 2 little things to work with. We have the summation of voltages being 0 and the individual value of the forward currents. So if we substitute the voltages by their more complete form, showing the relationship between the currents and the voltages, then we have the lower equation involving 4 voltages which algebraically sum to 0. Now, the first thing we notice here is that the thermal voltage, Vt, immediately cancels. It appears in all 4 terms, and therefore we can ignore it. We can also jump ahead and see that because I sub s occurs in the denominator of all of the logarithmic arguments, it too is going to cancel. So we end up with something much simpler, namely that the log of a product quotient argument is equal to 0, which means that the argument itself must be equal to 1, and it follows that the product of I1 and I2 must be identical to the product of I3 and I4. Stated differently, the product of the currents in the clockwise direction is exactly equal to the product of the currents in the counterclockwise direction. Now, in analyzing the bridge, we'll first introduce a temporary variable, x, and solve for the resulting currents. In general terms, they're as shown here. If we now substitute the values of the currents in that equation shown earlier, namely the one showing the products of currents in the two directions, we have the equation shown here. And in this particular instance, not that it's a very general result of great value, but in this particular case, x has the value shown in the final equation. Now we can go back and work out the conductance from the input point to the output point. We might first check, as in this example, that it really works as shown. We've shown 15 milliamps of current at the top, 10 milliamps at the bottom, and an input current of 5 milliamps. We solve for x in the bottom left-hand equation, and checking it out, indeed, the product of the counterclockwise and clockwise currents is indeed equal. So having done that, now we know the currents in the individual diodes, and we can calculate the net dynamic resistance from point A to point C in a very straightforward manner. Remember again that these are only incremental resistances, not ohmic resistances, so this will be a noiseless 6.5 ohm resistance. Well, since we're doing so well with diodes, let's stay with them for a while and take this one step further. Here we have 8 diodes, and we might start with agreeing on a numbering convention to make things a little easier. We can start at a particular point around the loop and name the currents sequentially, first in the clockwise direction, and then start at the same point and name the remaining currents and diodes in a counterclockwise direction. Notice that in some cases the currents flow into the network exclusively, in other cases exclusively out of the network, and in other cases the currents can flow either way. Now this isn't meant to represent a realistic network. The diode bridge, of course, is a real network. It's often used. But this is not. This is only meant to illustrate the notion of a loop of p-n junctions. As we'll see in a moment, those will actually be transistors, and the way we get the currents in and out of the loop will vary depending upon the particular circuit. But here's the basic idea. If we sum the voltages in the clockwise direction and equate them to the sum of the voltages in the counterclockwise direction, and then substitute the logarithmic form for those voltages, we now find in very general terms that the product of clockwise currents is identical to the product of counterclockwise currents. Now I should perhaps adjust that statement a little bit because it really isn't quite true. In practice, those junctions may have slightly differing areas and therefore slightly different I sub s. And we need to account for that in a more general analysis of a translinear loop. That's very readily done. The I sub s for a junction of area A is simply proportional to the area of that junction. Perhaps we should say, as a practical matter, it's not exactly proportional to area. There are subtleties, but certainly if those junctions are made, for example, as integer units, say of 2 junctions of identical size or 8 or whatever, then that would be true. In practice, there's a slight error in the relationship between the I sub s's and the current densities and the areas, but we needn't be too concerned about that at this point. So we end up with this expression shown at the bottom, that the saturation current for the kth junction is simply the area of the kth junction times a general variable, J sub s, which is characteristic of that particular doping profile, that particular junction type. So once again, if we substitute instead of I sub s a more complete expression for the saturation current involving its area, we find now that the proper representation is that it is the product of the current densities in the clockwise direction, which is identical to the product of the current densities in the counterclockwise direction. And that gets us to really the most important idea that we'll be talking about in this discussion. Namely, in its simplest embodiment, the translinear principle simply says that the product of current densities in a clockwise direction around a translinear loop is identical to the product of the current densities in the counterclockwise direction. Now, remembering that a real circuit may have areas which are not all identical, the junctions may not be all identical, we can account for that by extracting what is here called an area factor, which is simply the quotient of the areas in the clockwise direction divided by the areas in the counterclockwise direction. That factor can be used in correcting for the mismatches which occur unwittingly in monolithic fabrication, undesirably perhaps I should say, or we can actually deliberately introduce a non-unity area factor in order to achieve a particular kind of circuit behavior. Now, so far we've assumed the junctions are perfect. One of the first things that can go wrong with a practical junction is that it has associated with it some series resistance. In the case of a real two-terminal diode, this resistance can be quite troublesome because it's often very considerable. It represents the ohmic resistance of those portions of the junction leading up to the active region. So the forward voltage is the sum of the logarithmic component and a linear ohmic component, IF times R sub S. That's one of the reasons why we would rarely, if ever, use a diode in a translinear circuit. More likely, we would use a transistor connected as a diode. Before we do that, though, let's consider the consequences of the ohmic resistances surrounding an ideal transistor. In the center, we have the ideal transistor with terminals E dashed, B dashed, and C dashed. Connecting to those terminals are the what might be called approach resistances, most importantly the base resistance RBB dashed, the collector resistance RCC dashed, and in the emitter usually a rather small resistance REE dashed, which is often negligible, being sometimes much less than an ohm, very rarely more than 10 ohms. In this case, the base emitter voltage is the sum of a logarithmic term embodying the collector current and an ohmic component proportional to the emitter resistance and the effective resistance in the emitter circuit, RBB dash divided by beta. So now, connecting this device as a diode, we can see that the base resistance is only carrying a very small amount of the total forward current. In fact, it's typically 1/100th of the forward current, and the forward current isn't exactly IC. More exactly, the collector current is shown as beta over 1 plus beta times the forward current. Typically, about 99% of the forward current flows in the collector. So the very small amount of current flowing in RBB dash means that its contribution to the forward voltage VF is negligible in most cases. Likewise, the collector resistance, although it's carrying the full collector current, appears in a branch where a small amount of voltage drop is tolerable, unless, of course, the collector junction goes into forward bias, which would be equivalent to or corresponding to the transistor going into saturation. We would avoid that by the use of a sufficiently small current in the collector, or, of course, the use of a transistor of sufficiently large geometry. Now, let's look at some other ways of connecting a transistor so as to achieve diode-like behavior. This is a common connection for a transistor which we wish to behave like a diode. An emitter follower is added to provide current gain so that most of the applied current, called IC in the top left, actually does flow in the collector of the transistor. The base current of the current gain device is now beta squared, or 1 upon beta squared, I should say, times the collector current, and that might typically be 1/10,000th of the collector current, so we can more or less ignore it. Another thing that's happened here usefully is that the collector has been raised by VBE, so we can allow much more voltage drop across the collector resistance in the translinear device before running into saturation problems. Furthermore, we now have a robust node across which we can add further transistors to drive some subsequent part of the circuit. One practical problem with this circuit that needs to be taken into account is that there is a beta loop with two poles, and if not taken care of, this can be an oscillatory circuit. I don't plan at all to talk about dynamic effects today. It's of course a big subject, and it would require detailed discussion of each particular circuit on a case-by-case basis. So we will assume that in a practical design we'll take care of some of these dynamic issues with the appropriate additional circuitry. A yet further way of driving the so-called translinear device would be to use an operational amplifier. This is commonly done in high-precision circuits, obviously not so commonly done, rarely done in fact, in high-speed circuits. Nevertheless, it is an important modality, and we need to be sure that we understand what's going on here. In this case, we can assume that the bias current at the input of the operational amplifier is really very small. It can be picoamps quite readily. In fact, that could be an MOS operational amplifier, and that might be commonly employed in a bi-CMOS environment, for example. Now, the emitter current is supplied by the operational amplifier at its output, and any load currents are also absorbed at the output of the operational amplifier, and the collector current is very exactly equal to the supplied current, shown as IC at the top of the picture. Now we can drive any number of other transistors or other circuits from that base emitter voltage, which now is very exactly proportional to the logarithm of the collector current, or the current IC. In practice, we also need to worry about the stability of such a circuit. I won't say much about that here, except that commonly one would include a small network of the kind shown here to bypass the transistor at high frequencies so as to avoid a loop gain that is greater than 1. Most often the operational amplifier would be compensated internally for a loop gain of no less than 1. Now, getting back to that mysterious 7-transistor circuit, we're in a position now to understand how it works. In fact, it's very simple. In this case, there are two overlapping loops. Another aspect of translinear circuits is that they often do embody overlapping loops of this kind. In this case, we'll refer to the left-hand loop as loop 1 and the right-hand as loop 2, and consider them separately. Now, remember, the current that we're trying to evaluate or calculate or discover is the current I sub z. So for the time being, we'll assign a temporary variable A to describe that portion, that fraction of the current IZ which flows in Q3. And of course, the remainder of the current 1 minus A flows in transistor Q6. These currents recombine at the common branch in Q7, and so IZ flows in that device. Meanwhile, the left-hand pair of transistors, Q1 and Q2, are conducting equally a current IX, and the right-hand pair, Q4 and Q5, are conducting equally a current IY. So we can write the following, that for the first loop, we have the product of IZ being equal to the product of IX. For the second loop, the product of 1 minus IZ times IZ equal to the product of IY and IY. Summing those two equations, we find that I sub z squared is equal to I sub x squared plus I sub y squared. And it follows that the current I sub z is therefore simply the vector sum of Ix and Iy. Now we can check that out with an example. Supposing we allow Ix to be 3 milliamps, Iy to be 4 milliamps, and apply the vector sum to those two currents, then the result should be 5 milliamps. And indeed, if you check around the two loops, you'll find that this is in fact correct. This circuit might be of some value, for example, in generating the vector sum of two terms. One example that comes to mind is in the control of a state variable oscillator, where you might want to sum sine squared omega t and cosine squared omega t to produce a term which represents the amplitude of the two independent quadrature terms. In fact, in that case, you probably use some slightly different squarers. But this circuit is often referred to as a Pythagorator because it does solve the Pythagorean triangle. So, we've learned that translinear circuits are based on the unique relationship between the collector current of a transistor and its base emitter voltage. This relationship results in the transcon-ductance of a bipolar transistor being proportional to the collector current. I should mention also that this behavior is exhibited by MOS transistors in weak inversion. The operation of MOS transistors in weak inversion results in very slow device behavior, but in many cases, for example in neural networks, that is not a particularly important limitation. You can also reformulate the translinear principle for MOS transistors operating in heavy conduction, but it's not anywhere near as useful as the translinear principle for bipolar junctions because of its particular form. Let's now talk about probably the most popular application of the translinear principle, and that's translinear multipliers. There are really two ways that we can view translinear multipliers. In the traditional view, we would speak of the log-antilog approach. Log-antilog multipliers go back many years, probably to the very early days of bipolar transistors, and traditionally use operational amplifiers in a fashion similar to that I've mentioned already to force and sense collector currents. A somewhat different view is what might be called the integrated approach, in which voltage to current conversion, using circuits which we won't discuss today, first converts an input voltage into a pair of differential currents, followed by a differential current mode core, and then subsequently another step of current to voltage conversion. Let's talk first about the log-antilog approach. One way of thinking about a multiplier based on such techniques is with reference to the slide rule. This is my favorite slide rule from a few years ago. I hate to say how long ago. It's made in Germany, and it's a very nice tool for designing circuits. It's not quite in keeping with modern requirements, but nevertheless it still works. And the way it works is very simple. We have here two scales, each of which are marked off in a logarithmic fashion, beginning at 1 and ending at 10, and marked logarithmically in between. We would place the slide on the number, the first number in the two numbers to be multiplied. I'll point it here at 2, let's say. And then we can move our cursor back and forth on the central slide to the second number of the two we wish to multiply and read off the product once again on the first scale. The reason this works is because we've converted numbers into their logarithmic equivalent, added the logarithms, and then taken the anti-logarithm by referring back to the first scale. And in some senses, a bipolar transistor can be thought of as a microelectronic slide rule. It really behaves very much in the same way, and it's a useful icon to bear in mind. So this is how we might implement that idea. As discussed earlier, we can use an operational amplifier to force the collector currents. Here we have two currents to be multiplied, hence two operational amplifiers, each of which forces the collector current of Q1 and Q2. Maybe I should mention that the other terminal of the operational amplifier, assumed to have a differential voltage input, of course, would be grounded. So the collector of Q1 would be precisely positioned at ground, and likewise the collector of Q2 would be positioned at ground. As a consequence, the two devices operate at slightly different collector to emitter voltages, but that is not particularly important. What is important is that by virtue of the topology, we're going to add the voltages VBE1 and VBE2, and that's the first step in forming the product. So VBE1 plus VBE2 is expanded in this logarithmic form to the form shown at the bottom of the slide. And already we can see that the product IX, IY has been generated, but it's in a rather awkward form. It's associated with the saturation current and also associated with the thermal voltage. So in the next step, we'll get rid of that dependency by putting two more transistors into the circuit, Q3 and Q4. Q4 is going to be the output device. Q3 is driven by a further current, I sub Z, by operational amplifier OA3. Now, the bottommost node of this circuit is the sum of VBE1 and VBE2, and it's also the sum of VBE3 and VBE4, the negative sum really in both cases. Because we forced those VBEs to be equal, we once again have a simple translinear loop. The loop is closed across the ground connection. This is a rather non-rigorous way of showing the circuit really, because those two ground connections must be very exactly at the same potential. So once again, since the sum of VBE1 and VBE2 must equal the sum of VBE3 and VBE4, then we have this relationship where the product of Ix and Iy in the argument of the logarithmic term is equated exactly to the product of Iz and Iw in the second argument, because the VT's cancel and the I sub s's cancel. Once again, we're supposing that all the transistors have the same emitter area. Now, in this particular case, I might mention in passing that if the emitter areas were not all equal, this would result in a simple scaling error in this multiplier. It would not result in distortion. That's because this is only a one-quadrant multiplier. Ix, Iy, and Iz can only have one polarity, toward the operational amplifier or toward the collector of the transistor. It also brings to our attention a rather obvious need, but something that might be worth emphasizing, and that is that any multiplier must inherently be also a divider. Because if we're multiplying two currents, then in order to restore the output to the dimension of current, we must divide by a yet further current. And likewise, if the two inputs were voltages, then we must divide by a voltage in order to result in an output which is also a voltage. So that's the log-antilog view of the multiplier. In fact, we don't really need the operational amplifiers. This is a more highly integrated form, or really perhaps what I should say is this is the topology that we might start with if we were to approach this as part of a monolithic design. We still have the same four transistors. They're connected in exactly the same way as before, but we don't have the luxury of operational amplifiers to drive the various junctions. As you can see, on the left-hand side, we form the product of Ix and Iy in essentially the same way as before. And on the right-hand side, we have two junctions, one of which is operated at a known current, Iz, which is the denominator current, and the resulting current Iw represents the product of Ix and Iy. There are numerous ways in which this circuit can be changed around. We can do all kinds of interesting things with it. But for the time being, let's stick to our guns and think of it just as a multiplier. It can in fact be used, for example, as a squarer or as a divider or as a square rooter. However, as before, we can sum the voltages in the clockwise direction and the voltages in the counterclockwise direction and determine that the output current is the linear product of Ix, Iy divided by Iz. Now, we really don't want to keep referring to voltages. We've already established that we can analyze these translinear loops just in terms of currents. So from now on, we'll stop referring to the base emitter voltage. Of course, it's always going to be there, and there may be occasions when we would be concerned about its absolute value. For example, if we were designing the circuit to operate over a wide temperature range, we might be concerned about the increase in VBE at low temperatures, perhaps because of supply limitations. But by and large, translinear loops don't require us to think about voltages at all. We can analyze all the behavior in terms of input currents and output currents. Another reason why translinear circuits are valuable is because the impedances are as low as they ever can be in a bipolar environment. We don't use load resistors anywhere to establish the function. The resistances, if they really occur at all, are the incremental resistances, the transcon-ductances really, and those are as low as they ever will be for a given operating current. As a consequence, translinear circuits are very fast. We don't have to waste a lot of charge in moving, say, a collector junction. This is particularly important in a monolithic embodiment because the collector junction has a lot of capacitance associated with it most often, and by keeping these voltage swings to a minimum, the circuit speed can be maintained. The original translinear multipliers were made in 1968 on a relatively prosaic process at that time, and yet they still achieved bandwidths of the order of 500 megahertz. Now, the next step in approaching the more familiar translinear multiplier would be to replace the individual currents, the one-quadrant currents, with pairs of currents which are complementary. In fact, here there's only one pair of currents at the input, and that is the pair 1 plus x I sub x and 1 minus x times I sub x. and a fixed current shown as 2IY, which is supplied to the common emitter node of Q1 and Q4. We're interested in determining the output current, in this case again in differential form 1 minus YIY and 1 plus Y times IY. And we can do that by directly applying the translinear principle, again without any reference to the voltages. In the clockwise direction we have 1 plus X IX times 1 minus Y IY. In the counterclockwise direction 1 minus X times IX times 1 plus Y IY. And if we solve that very simple equation, we'll find that Y is always equal to X, no matter what IX and IY might be. That's nice because it means that we can make IY very large and result in a high gain or a high output from the two free collectors, or we can make IY small and result and achieve attenuation. So we can use this thing as a gain control element, perhaps. In practice, those transistors may not match perfectly. So we can account for that by including each of the emitter areas, shown here as A1 through A4, explicitly in the equation, leading to the area factor, which we mentioned earlier, as in this case A3 times A4 divided by A1 times A2. This results in parabolic distortion, and you can do the derivation for yourself, but we might just look at the consequences of such distortion. If we were to take those equations and analyze the effect of emitter area ratio errors, we'd find that Y isn't quite equal to X as we thought, but a term sigma, which I'll define in a moment, plus X minus sigma X squared, where sigma I'll define as 1 minus lambda over 1 plus lambda. And clearly, if lambda is 1, that means the area ratio, or the area factor I should say, is 1, then sigma is 0 and Y becomes equal to X again. Whenever it's not quite equal to 1, then we have some errors. It might be worth mentioning too that the area factor can be 1 even if the junctions are not the same size, provided that they're the wrong size in the right way. I think you can see what I mean. We have the product of A3, A4 divided by A1, A2, and there are numerous ways of making that 1. So we don't have to use junctions all the same size. So what's going to happen here? Well, first we can see there's going to be a DC error. That is, even when X is 0, I should mention that X and Y are bounded between minus 1 and plus 1. So when X is 0, corresponding to the balanced condition at the input, then there's still an offset term sigma. And in general, there is a parabolic component of X which represents parabolic distortion. If we were to simply plot the input and output, where X varies from minus 1 to plus 1, and Y likewise varies from minus 1 to plus 1, then we'd find that we might see something like this instead of the desired linear relationship, and this is the offset sigma, and the parabolic form of the distortion is evident. This is quite troublesome in practice, and it's compensated for in a number of ways. First, by very careful layout. Most often these multiplier cores are made by overlapping quads of transistors so as to eliminate processing gradients and thermal gradients across the chip. In advanced monolithic circuits, sometimes we use laser trimming to deal with the VBE errors. In practice, the distortion can be of the order of 0.05%, even without trimming, and very much lower than that with trimming. So whilst it is of some concern, it certainly isn't a devastating defect. There are really only two ways in which 4 transistors can be connected in a translinear loop. In type A can be thought of as referring to alternating because the junctions alternate clockwise and counterclockwise around the loop. The connection form is shown here. We haven't yet discussed a multiplier based on this form, The form we have discussed might be called type B, which can be thought of as standing for balanced, in which case we have two clockwise connected junctions on the right and two counterclockwise junctions on the left. The drawing at the bottom here is a more typical way of showing that connection. Nodes N2 and N4 will be driven by a pair of differential currents. Node N3 will be driven by a variable current, which sets the gain of the multiplier, and the outputs, of course, will be taken from I3 and I4. Notice in passing that in this case, currents I1 and I2 are available for reuse, and a circuit which we won't discuss this time around is the gain cell, in which those currents are in fact added back together again in phase to realize a very compact current mode amplifier. Now let's look at a type A circuit again. Here we have two diode connected transistors on the outside and a simple differential pair in the center. Now this circuit has a very interesting property which leads me to call it a beta immune circuit. I'll explain what I mean in just a moment. First, let's analyze that using the translinear principle as before. And once again, we find that given that all the junctions have the same emitter area, or that the emitter areas are adjusted so that the area factor is still unity, then the output modulation index Y is identical to the input modulation index X. The beta immunity arises in the following way. In fact, we can analyze this intuitively, although it's better to do this more accurately and more rigorously, but just look at the way this thing behaves. Let's suppose for the moment that the base currents of Q2 and Q3 really don't matter. And in fact, the output modulation index Y is identical to the input modulation index X. If that is the case, the proportion of current being diverted from the input branches to the bases of Q2 and Q3 is always in exactly the same ratio, bears the same ratio as the input currents themselves. And that just means that we have effectively changed the value of the bias current Ix, which doesn't change the relationship between X and Y. It's a kind of a hokey circular argument, perhaps, and it doesn't take more than a couple of lines of algebra to prove for yourself that no matter what beta is, the modulation index at the output is independent of the base current. Now there's a subtle sort of caveat to that. Clearly, if beta is finite, then not all of the tail current, 2IY, appears at the collector. So there is an alpha error, and it may sound like a fine distinction to say that there's an alpha error but no beta error. But what I want to show is the following. If we were to make an amplifier using this principle and plot its gain as a function of the tail current shown along the horizontal axis here, we'd find that it was an exact function of the tail current right up to the beta point. Now here we've assumed a beta of 100, and that means that we can get a current gain of 100 out of the circuit before suddenly the gain stops increasing and it plateaus at a gain of 100 no matter how large the tail current is. That may not seem very remarkable, but it's the only circuit, certainly to my knowledge, that exhibits this property. You might think about that and discover for yourself why it is so, and compare it with the type B configuration, which not only does not exhibit this behavior, but in fact exhibits quite significant beta dependence. Okay, now we need to talk a bit more about the more common four-quadrant form of the multiplier. So far, we've shown a two-quadrant form. That means that the input is in the form of a pair of differential currents, and some third current, the tail current, determines the magnitude of the output. But the output always has to be in the same polarity. In order to produce an output that can have either polarity, we need to use a full four-quadrant form. This is a classic 6-transistor translinear multiplier, which really is, again, two overlapping loops. The first loop consists of Q1, Q2, Q3, and Q4, and the second shares Q1 and Q2 and consists of Q1, Q2, Q5, and Q6. If we apply the translinear principle to both of those two loops independently, we discover quite quickly that the output modulation index W is identical to the product of X and Y. This is a very powerful circuit. It's very widely used. Its power arises from the fact that, first, the currents can have any value over a very wide range of values from nanoamps up to many milliamps. The behavior is exactly the same. It's independent of the exact bias currents. Also, as I mentioned earlier, the voltage swings are very small and the circuit can be therefore very fast. Typically, the difference in base voltages might only be 50 millivolts full scale. That's not altogether an advantage. It means that the circuit is fast because the displacement currents in parasitic capacitances are small. It also means, of course, that noise voltages generated in the base resistances of those transistors can be quite troublesome. And in practice, the design of high-precision translinear multipliers requires a lot of attention to base resistance. But again, it's not an insuperable problem. So let's look at a few examples of some typical products that make use of these principles. This is a micro photograph of the 8534, an accurate general-purpose four-quadrant multiplier introduced about 15 years ago. It was notable at the time in that it was complete, required no external components, and it was the first such product designed to take advantage of laser wafer trimming to eliminate all the major sources of error. Here, illustrative of the high-speed capabilities of translinear multipliers, is the 8834, which was introduced about 2 years ago. It has a bandwidth at the chip level of about 1 gigahertz, although in fact the useful frequency range is limited by the package to perhaps 500 megahertz. At the recent International Solid-State Circuits Conference, many companies were reporting translinear multipliers with frequency ranges up to several gigahertz using recent technologies. In another direction of improvement, this product, the 8734, incorporates laser trimming to eliminate not just the input and output offsets and set up the scale, but also to minimize all harmonic distortion terms to about minus 80 dBs. In this case, by trimming out the VBE errors, which lead to even-order distortion, and ohmic errors, which lead to odd-order distortion. This part's also interesting because it can be used as a very accurate two-quadrant divider with a 1,000 to 1 denominator range and a 200 megahertz gain bandwidth product. Using the term translinear in its broader context, here we see an example of a highly accurate translinear network which generates the sine or cosine of an input with an unusually large angular range of plus and minus 500 degrees. By incorporating two such networks on this chip, all trigonometric functions and many of their inverses, such as the arctangent, and some less common functions, such as the versine, can be generated using just pin strapping to alter the function. Finally, here's a more recent example, a dual-channel, low-noise, variable gain amplifier for ultrasound applications. Its principle of operation doesn't rely directly on translinear behavior of devices, but the analysis of its special behavior is facilitated by knowing that the bipolar devices used to achieve the variable gain do in fact exhibit this unique proportionality of transcon-ductance to collector current. In this brief presentation, we've only had an opportunity to discuss a few translinear circuits. There are many other ways that transistors can be connected in a loop of junctions. There are many other ways in which overlapping loops can be used to elicit higher order functions. Most importantly, in a modern context, there are many other device types available as well. We've limited our discussion to the NPN transistor, but it will be obvious that PNP transistors can be used in just the same way. That is to say, high-quality PNP transistors which have been designed for accurate translinear properties. Lateral PNP transistors don't count. They behave very badly in this case. Also, we have CMOS transistors, and very often we would find ourselves designing in a bias CMOS environment where we can take advantage of the MOS transistors for biasing and perhaps voltage to current conversion, and the high-quality bipolar transistors for the translinear portions. So there's much more that could be said about translinear circuits. That'll have to await a further opportunity at some time in the future.